Well, now that we know how to do a 2-sample t interval, what about a 2-sample t-test? Well, fortunately for us, the conditions are going to be exactly the same as they were for the interval. So we won't have to spend a whole lot of time remembering what are the conditions for a 2-sample t-test, because they're the same conditions we just went over for a 2-sample t interval. We have to check, is it an SRS? They tell us or they don't. Is it independent? Is the population at least 10 times the size of the sample? But remember, when we're dealing with 2 samples, we have to test them for both. And is it normal? Do they tell us they're both normal, or are both n sub 1 and n sub 2 greater than or equal to 30? Central limit theorem. Okay. Same exact conditions that we did last section in the interval. Now we need to calculate the t-test statistic. And you can see this beautiful looking statistic right here. Why is it -0? Because the null is always there is no difference. So if the null mu sub 1 minus mu sub 2 is equal to 0, then why are we going to write it in when we know the answer is 0? If I'm subtracting 0 from a number, it doesn't change the value. So that's where this 0 is here. You can just forget about that altogether. Okay. So what are our choices for alternatives? Well, it could be that mu sub 1 minus mu sub 2 is less than 0. Or it could be that mu sub 1 minus mu sub 2 is greater than 0. Or it could be we want to test that they are not equal to 0. Okay? Remember, we could also write these another way. We could write that mu sub 1 equals mu sub 2, or that mu sub 1 is less than mu sub 2, or that mu sub 1 is greater than mu sub 2, or that mu sub 1 does not equal mu sub 2. Okay? So that's our null and alternative. Now here's our t-test statistic. It's the difference between the sample, x bar 1 minus x bar 2, over the square root of s sub 1 squared over n1 plus s sub 2 squared over n2. So this should look very, very familiar. Here's the mean, and here's the standard deviation. We need degrees of freedom. How do we know it's degrees of freedom? Because it is a t. If it's t, we need degrees of freedom. And here, just like in the confidence intervals, the degrees of freedom is the smaller of n sub 1 minus 1 and n sub 2 minus 1. Whichever one's smaller, that's the degrees of freedom that we must use. Okay. Well, let's look at this once again. Does increasing the amount of calcium in your diet reduce your blood pressure? Examination of a large sample of people revealed a relationship between their calcium intake and their blood pressure. Researchers therefore diagnosed a random comparative experiment. The subjects were 21 healthy men who volunteered to take part. They were randomly assigned. There's where we're going to get our randomness from. 10 of the men received calcium for 12 weeks, while the control group received a placebo that looked identical to the calcium for 12 weeks. The experiment was double-blind. The response variable is the decrease in their systolic blood pressure for the 12-week period. An increase appears as a negative number. So the decrease would be the positive number, and increase would be the negative number. Do the data provide convincing evidence that the supplement reduced blood pressure more than the placebo on average? Well, let's find out. So what is our null hypothesis? Always, always, always our null is there is no difference. So our null would be that mu sub calcium is equal to the mu of the placebo. What's our alternative? What do we expect is going to happen? Oh, that the calcium group is going to have a larger decrease in their blood pressure. It's kind of confusing the way this one is worded. If you guys prefer it the other way, you might see this. They're saying the same thing. That's our null and our alternative. But the null and alternative are meaningless unless we define the parameter. So what is mu sub c? Okay. It's the true mean decrease in blood pressure for men who take calcium supplements. Okay, the true mean decrease in blood pressure for who? Men who take calcium. What is mu sub p? The true mean decrease in blood pressure for men who took the placebo. All right. So what are we going to do? Oh, this is a 2-sample T test. We're going to run a 2-sample T test. So we define the parameter. I didn't write my second one, but you guys can write the true mean decrease in blood pressure for men who took the placebo. State the null and alternative, and then explain what test we're going to use. Are we allowed to do this problem? Well, it tells us random somewhere in here. The men were randomly assigned to the groups. So cool, it's an SRS. Independence. Are there more than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? 10 times 10. Are there more than 100 men who take a calcium supplement? Yeah, I'm sure there are. 11 times 10. Are there more than 110 men who don't take a calcium supplement? Yeah. So we're okay for independence. Normality. They don't tell me it's normal. And n's not large enough to use the central limit theorem. What do we have to do? This is where we have to put the data in a list and make a graph. And we're going to look at the graph and see, is there strong skewness or outliers? And if there's no strong skewness and no outliers, we're okay. And we can say that the data is approximately normal. So I could type all of these into my lists and have it do side-by-side box plots. And I should have done this beforehand, but I wasn't all the way prepared for this. So stat, edit. Okay, so 7, -4, 18, 17, -3, -6, 1, 10, 11, -2. All right, there's the data for the calcium group. And let's go to list 2 and put in the data for the placebo group. -1, 12, -1, -3, 3, -5, 5, 2, -11, -1, and -3. Now I'm going to make side-by-side box plots so that I can take a look at these graphs and see if the data is roughly symmetrical without any outliers. If so, then I can assume the normality condition has been satisfied and I can move on and use my table and my test statistic formulas if the data is roughly symmetrical without any outliers. So I'm going to go into stat plot. And I wanted to do 2 graphs at the same time. So I'm going to go into plot 2 and I'm going to turn it on. I'm going to go back to plot 1 and tell it what I want it to do. I want it to make a modified box plot of list 1. Cool, it's already there. You can see how it's highlighted there. And it's turned on. So I'm okay there. Now, I'm going to go to plot 2, maybe. Doesn't want to let me go to plot 2. So I'm going to go back into stat plot. For whatever reason, it doesn't want me to do it. And I'll go to plot 2 this way. So I'm going to go into plot 2. It's turned on. I want it to make a modified box plot. So I tell it modified box plot. And I want it to do list number 2 so that I get both plots. And I'm going to say graph. Oh, I can't really see it. Remember zoom stat, which is zoom 9. What in the world happened? When you see a graph that looks like this, you know you put a data point in wrong. So I need to go back and look at the original data set, the blue one, and see what happened. Oh yeah, check it out. Down here, I typed in 111 instead of 11. No wonder. Now let's see what this looks like. When I graph, it's not going to show me what I want. So remember, we can always fix that with Zoom 9 or Stat Zoom. There we go. Both of these look roughly symmetrical. Whew. Cool. So I know that I'm allowed to do this problem now. I should make a sketch of those two on my problem here. Okay, so I should sketch those two box plots showing that the data is approximately normal. Therefore, it's okay for me to move forward. Now I need to calculate the test statistic. So I've checked my conditions and it's okay. I've told the reader what I'm about to test. Now I'm going to test it. T equals x bar 1 minus x bar 2 over the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. But I don't have any of these data points yet. All I have is this data in a list. So I need to get all of this out of my calculator. So if I go to stat, calc, I want it to do two variable statistics. It's going to say on what lists. So yeah, please do the work on list 1 and 2. And then calculate. Oh, that didn't work. Sorry. Stat. So when this happens, you're going to have error come up. Oh, it's because the lists aren't the same size. So I'm going to do for sub 1 first. So go in here. All right, I can see I got the lists. The data's in L1. Go to stat, calc, 1 var stats for list 1. And it tells me that the mean is 4.9. And it tells me the standard deviation is 8.875. And it tells me that n is 10. All right, now I'm going to do it for the second one. Stat, calc, 1 var stats of list 2. List 2. Never, ever, ever mess with frequency list. Tell it to calculate. And so list 2 is negative 0.2727. So it's minus negative 0.2727 over the standard deviation, which is 5.9 squared, divided by n sub 2, which is 11. So that's my t-test statistic. I'm not sure why it's cut off down there, but I plug all these numbers into the calculator. I let it do all the work for me, and it comes up with 1.604. But I can't find my p-value until I look up degrees of freedom. Remember, it's the smaller of the two. So it's 10 minus 1 equals 9. I have 9 degrees of freedom with a t-test statistic of 1.64. So now I need to look on table B to find out what my p-value is. So 9 degrees of freedom, 9. Now I need to trap 1.604, 1.604, it's right here. So my p-value is between 0.05 and 0.1. So my p-value, I don't know exactly what it is, but it's larger than 0.01, 0.05, but smaller than 0.1. So let's figure out what the exact p-value is. The only way to get the exact answer for the p-value is by calculator. all we can do is use table B to find a range of the values for the p-value, but we can't find the exact p-value without using the calculator. So let's go to stat test. What kind of test is it? Oh, it's a 2-sample t-test. Do I have data? Yes. I put the data in my lists. What lists? L1 and L2, yes. And then it's going to ask me, never ever mess with frequency. It's going to ask me, what is my alternative? And we decided that the alternative was going to be greater than. So, whoops. So I go over here and I select greater than. And then I come down here and I say, all right, cool, do the work. And it gives me a t-test statistic of 1.55. It gives me a p-value of 0.0699. Yeah, that makes sense. If the p-value is 0.0699, that fits nicely in what I found when I did it by hand. Is that data statistically significant? No, not at the alpha 0.05 level, it's not. So let's finish this problem up by interpreting our results in context. So again, p-value is equal to 0.0699. Since the p-value is greater than the alpha level, we fail to reject the null. We do not have enough evidence to conclude that taking calcium reduces blood pressure. The data is not statistically significant. Therefore, we cannot conclude that these calcium supplements will reduce your blood pressure.